Today, we will learn how to select fans and the shape of the ducts around the fan. You should select the types and models of fans based on their purpose of use. You should also select fan motors based on their static pressure and airflow rates. Basically, select centrifugal fans to use for office air conditioning equipment and ventilation equipment. In general, choose thoraco type fans and limit load type fans, but not diagonal flow type fans and axial flow type fans. If a small quantity of airflow is required, select pipeline type axial flow fans. If axial flow type or diagonal flow type fans are selected for an office, you must pay attention to the sound. For factory air conditioning, axial flow type or diagonal flow type fans are often selected. When you select fans, use fan selection guides distributed by manufacturers to decide the blade size and power based on drops in pressure and airflow rates in the duct system. The fan selection guide on this slide was prepared assuming that the temperature of the air is 20 degrees Celsius and the weight is 1.2 kilograms per cubic meter, which are standard conditions. If air at a significantly high temperature is to be sent, you should correct the static pressure and shaft power. If you select electric equipment, including fans, make sure to use the appropriate power supply frequency of either 50 Hz or 60 Hz. When you select fans, you have to consider the noise. Referring to a previous slide, I said that if axial flow type or diagonal flow type fans are selected for an office, you must pay attention to the sound. For fans, you must consider the noise. In advance, confirm the permissible noise level in the room where the air should be conditioned. Also confirm the noise generated by fans. Consider what kind of fan should be used, where the fan should be set, and how the fan should be installed. In principle, it is the best to install it in a place, like a machine room, so that the noise and vibration do not badly affect the room to be air conditioned. Fans are often installed above ceilings. Even so, select fans which make less noise, such as sound-absorbing box type or sound-muffling type fans. In particular, if you select axial flow type fans and diagonal flow type fans, you should pay extra attention to the design. Numeric values corresponding to the noise toward a duct and the noise toward the equipment side are indicated in the blocks for noise level. If you calculate noise, use the value corresponding to the noise toward the equipment side. You should also pay attention to the following points. Basically, fans should be set on the floor. Vibration isolators are needed to reduce the vibration caused by the fan. If you select small fans, they can be hung from the ceiling. If you select large fans, it is impossible to hang them from the ceiling, so you have to consider where such large fans should be set. According to relevant standards set by the Ministry of Land, Infrastructure, Transport and Tourism, you may hang fans whose size is number 3.5 or smaller. If you install fans outdoors, you should specify the outdoor type motors to be used in the equipment list. If 400 feet or higher level motors is used while noise are controlled by inverters, the temperature of motors may rise abnormally. You must therefore specify to use high voltage reinforced insulated motors for inverter drive in the equipment list. If you install fans in a room where fire is used, select overhanging type fans to discharge the air. Do not select any fans, such as axial flow type fans, whose bearings are along the path of the airflow. If you use an axial flow type fan with bearings inside, oil adheres to the bearings when the air is discharged by the fan, so you will have a lot of trouble cleaning it. A classification table of fans is shown on this slide. For air conditioning, thoraco type and limit type fans are generally used. Thoraco type fans are commonly used for up to 1300 pascals of static pressure. Limit load types are commonly used for over 1300 pascals of static pressure. In most cases, thoraco type fans are selected. If a small quantity of airflow is required, pipeline type fans are also used. Next, from the design and construction do's and don'ts of the conduit system, I will explain the shape of the ducts around the fan. At the design stage, you need to consider the shape of the ducts around a fan in detail. If the shape of the ducts does not fall within conditions which I will explain next, the ducts will become too resistant. Fans may not send the required airflow, and the ducts may vibrate. As a result, ducts and fans may break. Fans must therefore be designed assuming the shape of the ducts to be used. Looking at this slide, let's review how to install a damper at the fan outlet. The damper shown on the left side is a bad example. A damper is installed at the fan outlet. This damper is used for airflow adjustment. The wind velocity at the fan outlet is not clear. In addition, the fan outlet duct is not extended. The damper axis is sideways from the direction of the revolution of the fan blades. In this case, the wind velocity is faster at periphery positions more distant in the direction of the centrifuge from the center of the fan blades. If duct blades are installed so that the axes of the duct blades are sideways from the direction of the revolution of the fan blades, inner blades receive the wind at lower speeds, while outer blades receive the wind at higher speeds. Different forces are therefore applied to every blade. As a result, excessive force is imposed on the damper and may cause breakage. In such a case, you should take measures as shown in the chart on the right side. At the fan outlet, the cross-section area of the duct should be extended so that 1 pascal per meter of pressure loss can be attained, because the constant pressure method is adopted. In addition, a damper should also be installed. Even if the cross-section area is extended to enable the duct to gain 1 pascal per meter of pressure loss, when the airflow rate is over 10,000 cubic meters per hour, the wind velocity is faster than 8 meters per second. Next, direct the damper axis in the lengthwise direction of the revolution of the fan blades. If the damper axis is in the lengthwise direction of the revolution of the fan blades, every damper blade receives the same pressure. Select opposing blades when dampers are used for airflow control. If blades are used to open and close a damper, select parallel blades. Adopt either opposing types or parallel types based on how dampers are used. Some manufacturers distribute parallel blade dampers as a standard. Check the type of damper before construction. Now, let's learn the rules for turning the direction of the duct around the fan outlet. About example is shown in the drawing on the left. The direction of the outlet duct of a fan is turned in the opposite direction of the revolution of the fan blades. If a duct turns in the opposite direction of the revolution of the fan blades, the flow rate changes greatly. As a result, the resistance in the duct increases. If the resistance in the duct increases and the required flow rate is not given, excessive energy is used. In addition, such situations may cause fans to generate vibration and noise. In the worst case, fans may break. In such a case, take measures as shown in the drawing on the right side. Extend the cross-section area of the duct. In other words, make the wind velocity slower. It is best if the duct behind the fan outlet is straight. To make it straight, you should adopt pedestals with longer legs or those hung from the ceiling. It is, however, difficult to do so. In that case, if the duct should be turned, turn it in the direction of the revolution of the fan blades. For a fan on the right side, the fan blades revolve clockwise from the suction side. Order fan blades that rotate counterclockwise and set the direction of the revolution of the fan blades towards the duct to be turned. It is good to consider the use of guide vanes. If the cross-section area of the duct is extended so that 1 pascal per meter of pressure loss can be attained, guide vanes are not required, because the wind velocity is 10 meters per second or slower. You should, however, confirm whether they are necessary or not. If you design the cross-section area of the duct to be extended so that 1 pascal per meter of pressure loss can be attained, you can solve problems regarding the wind velocity. Now, I will explain about how to take measures when fan outlets are opened or connected to a chamber. A bad example is shown in the drawing on the left. The outlet of fan A on the left side is open without a duct. The outlet of fan B on the left side is connected to the chamber without a duct. The cross-section area of fan B is suddenly extended. The resistance in the duct therefore increases. In such a case, you should design the fan outlet as shown in the drawing on the right side. You should design the cross-section area of the fan outlet side to be extended so that 1 pascal per meter of pressure loss can be attained. In addition, the extension angle should be 30 degrees. Speaking of the open area of the duct, remember to design it to have a wire gauge attached. The wire gauge will prevent accidents due to alien materials entering the fan. Now, I will explain about ducts for fan outlets when 2 fans are arranged in a row. A bad example is shown in the diagram on the slide. If a duct, as shown on the upper left side, is used when 2 fans are operated at the same time, the duct is likely to break. If only one of the fans is operated, a part of the air flows in the direction of the other fan not in operation. In such a case, design ducts as shown in the drawing on the right side. Design a curved duct to be connected to the main duct, as shown on the slide. If it is difficult to design such a duct, you should consider taking other measures. For example, you could install a motor damper to be used in the operation and shutdown of the fans. You may also install a check damper to prevent the air from flowing back. Now I will explain about outlet ducts for centrifugal fans. About example is shown in the diagram on the left side. In this case, an extended duct is installed at a fan outlet. The cross-section area of the duct is extended compared to that of the fan outlet. The extension angle of the duct, however, is over 30 degrees. Not only suddenly narrowing ducts but also suddenly extending ducts offer great resistance. In such a case, you should design the duct as illustrated on the right side of the slide. The cross-section area of the duct on the fan outlet should be extended so that 1 pascal per meter of pressure loss can be attained. The extension angle should be 30 degrees or less. If you cannot design the duct to have an extension angle of 30 degrees or less, attach the guide vanes to the duct. If the wind velocity is 10 meters per second or less, guide vanes are not necessary. If the duct must be turned just behind the fan outlet, or if a straight duct cannot be connected to the fan outlet, you should install guide vanes. Now I will explain about ducts at outlets of high static pressure type axial flow fans. A bad example is shown in the drawing on the right side. The fan connected to the duct is a high static pressure type axial flow fan. Fan outlets are connected directly to rectangle to round ducts or via short straight ducts with a length of less than 2.5 d to round elbow ducts. If ducts are structured like this, the airflow may be significantly reduced and the duct may vibrate. You should note that the performance of an NJA axial flow fan greatly changes based on the shape of the area around the fan. In such a case, you must design the relevant duct to be connected to the fan as shown on the right side. The do's and don'ts introduce a method where a standard extension cone is attached before a rectangle to round duct is connected. The length of a short straight duct is recommended to be longer than 2.5 d. If the length is 2.5 d or less, guide vanes should be installed on the elbow. For more, look at the next slide. The section for NJA axial fans in the technical data book provides further information. Design the area around fans by referring to this slide. NJA fans, a type of high static pressure type axial flow fan, include SF fans and large size axial flow fans. First, consider the case where a straight duct is used on the discharge side. For SF fans, a rectangle to round duct is used. If the diameter of a fan is represented as d, the length of a rectangle to round duct is up to as long as approximately 0.7 d, or 300 millimeters or longer. The size of a duct may be the same as d if a 4-pole motor is used. If a 2-pole motor is used, however, the extension angle of one side is within 15 degrees, or that of both sides is within 30 degrees. If a large-size axial flow fan is used, a rectangle to round duct, whose dimensions are the same as the fan, is installed at a length of approximately 0.7 d, and an extended duct is installed. A standard extension cone can be installed. Among large-size fans, the compact-type fan has an outlet opening 2 sizes larger than the base of the outlet, so a standard extension cone can be connected to it. If a curved duct must be connected to a fan outlet, design the duct as shown in the drawing on the slide. For SF fans, If the length of the rectangle to round duct is approximately 0.7 d, a curved duct can be directly connected to the fan outlet. If you want to connect a curved rounded duct to the fan, you should design the round duct to be connected to the fan through a straight duct or extension duct with a length of approximately 0.7 d. In both cases, if a 4-pole motor is used, the diameter of the duct to be connected may be the same as that of the opening on the suction side. A straight duct also may be used. If a 2-pole motor is used, the extension duct with an extension angle of 15 degrees on each side must be selected. For large-size axial flow fans, a curved rectangle to round duct can be connected to the fan through a standard extension cone. If the wind velocity in the duct is faster than 18 meters per second, small pitch guides must be attached to where the duct is curved. Low-velocity ducts are used as air conditioning ducts. Design fans so that the wind velocity in the duct is not faster than 10 meters per second. Next, if a chamber is connected to the discharge outlet of an SF fan, design it so that the chamber is connected to a rectangle to round duct with an opening 2 sizes larger than the base of the fan outlet. You may design the chamber to be connected through an extension cone to the rectangle to round duct. For large-size axial flow fans, a chamber should be connected through a standard extension cone to a rectangle to round duct. A canvas duct can be designed to be connected directly to an SF fan. On the other hand, note that a canvas duct cannot be directly connected to a large-size axial fan. A canvas duct should be designed to be connected to the fan through a standard extension cone. A canvas, however, can be connected directly to the fan. You must carefully design a duct to be connected to a high static pressure type axial fan. NJA axial flow fans are highly efficient and save energy. Bad duct design, however, causes the fan blades to break. So you must be very careful when you design an NJA airflow fan system. I will explain how to install ducts on the suction side later. Now, I will explain about outlet ducts of low-pressure type axial flow fans other than NJA fans. A bad example is shown on the left side of the slide. An extension duct is installed at the fan outlet. The extension angle of the extension duct is over 30 degrees. Not only suddenly narrowing ducts but also suddenly extending ducts offer a great resistance. The length of the straight duct on the outlet side is less than 2.5 d. This is also a cause of increased resistance. In such a case, you should design the duct as illustrated in the right side on this slide. The cross-section area of the duct on the fan outlet should be extended so that 1 pascal per meter of pressure loss can be attained. The extension angle shall be 30 degrees or less. If you cannot design the duct to have an extension angle of 30 degrees, you should attach design guide vanes to the duct. If the wind velocity is 10 meters per second or slower, guide vanes are not necessary. If the duct must be turned just behind the fan outlet, or if a straight duct cannot be connected to the fan outlet, you should use guide vanes. Except for NJA fans, therefore, the shapes of ducts in low-pressure type axial flow fans may be based on those in centrifugal fans. Now, I will explain about inlet ducts of centrifugal fans. A bad example is shown on the left side of the slide. The depth of the chamber on the fan suction side is shorter than 3/4 of the suction diameter D. In such a case, the resistance rises and interrupts the flow of the air and causes noise. In this case, you should take measures as shown on the right side of the slide. The cross-section area of the duct on the fan suction side should be extended so that 1 pascal per meter of pressure loss can be attained. If a straight duct is used on the suction side, its length should be twice as long as or longer than the height of the duct on the suction side. If there is an elbow just before the suction outlet, support guides must be installed. If the length of the straight duct is sufficiently long, support guides are not necessary. If a chamber is installed on the suction side, the depth should be longer than the suction diameter. If the suction wind velocity is slower than 6 meters per second, the chamber depth may be relatively shorter. The suction wind velocity may be up to 12 meters per second, but you must not design fan systems to be imposed with unreasonable airflow resistance. Now, I will explain about inlet ducts for high-pressure type axial flow fans. A bad example is shown on the left side of the slide. One of the bad points of duct connection to fans is that there are no devices on the suction outlet open to the atmosphere. The duct width suddenly narrows toward the opening. A rectangle to round duct is directly connected to the fan suction outlet. Bell mouths or cones recommended by manufacturers must be used for high static pressure axial flow fans. Another bad point is the shortness of the straight duct to be connected to the curved duct on the suction side. This shortness also raises the airflow resistance, which interrupts the flow of the air and causes noise. You must be careful if you want to use high static pressure type NJA axial flow fans, because they are very efficient. The do's and don'ts advise you to use a bell mouth at the suction outlet if it is open to the atmosphere. Also use bell mouths or cones if a chamber is connected to the duct. After a rectangle to round duct is installed on the fan suction outlet, the duct must be connected to it. If an elbow is used on the suction side, the length L must be 5D or longer. If a lobster back elbow consisting of 4 pieces or more is used, the straight duct length L must be 3D from 4D. If an elbow with guide vanes is used, the straight duct length L must be 2D or longer. Therefore, be sure to use a straight portion and connect it to the fan suction outlet. For more, see the next slide. First, if the suction side is open to the atmosphere, the centers of both SF fans and large-size airflow fans must be 0.8 D away from the chamber walls, and bell mouths must be attached. For safety, a wire gauze should also be attached. For large-size axial flow fans, if the fan center cannot be positioned 0.8 D away from the chamber walls, a rectangle to round duct with an opening 2 sizes larger than the duct base should be connected to the fan. For safety, a wire gauze should also be attached. If a chamber is connected to a duct connected to the fan suction outlet, you can take the same measures for both SF fans and large-size axial flow fans. But different measures should be taken based on whether the fan center can be positioned 0.8 D away from the chamber walls or not. If the fan center can be positioned 0.8 feet away from the chamber walls, the fan can be installed in the chamber. In this case, a bell mouth should be attached inside the chamber. Bell mouth can be also attached outside on the chamber. In addition, a rectangle to round duct with an opening 2 sizes larger than the duct base can be connected to the fan. In any case, a wire gauze should also be attached. For both SF fans and large-size axial flow fans, if the fan center cannot be positioned 0.8 feet away from the chamber walls, the chambers must be connected through a rectangle to round duct with an opening 2 sizes larger than the duct base of the fan. For SF fans, if the path of the airflow must be turned on the fan suction outlet side, a rectangle to round duct with a length of 7D can be connected to the fan. Bell mouths are not used. On the other hand, for large-size axial fans, the airflow path can be turned by connecting a rectangle to round duct to the fan through a standard extension cone. Bell mouths are also not used in this case. Canvas ducts must not be connected directly to SF fans and large-size axial flow fans. They should be connected to the fans through extension cones or rectangle to round ducts. For SF fans, the distance between a bell mouth and the chamber walls on the suction side should be 0.8 D or longer. Also, for large-size axial flow fans, the distance between a bell mouth and the chamber walls on the suction side should be 0.8 D. If possible, make the distance longer than 1 D. Finally, if high static pressure type fans are operated parallel to each other, ducts are connected between SF fans and large-size axial flow fans in the same way. In the case where chambers are shared in front of and behind fans, there are no problems if there are differences in the number of fans and sizes of fans. Select, however, fans which have the same range of operating pressure. Ensure a distance of 0.8 D between the center and chamber walls of the fans, and 2 D between each fan. If some fans stop operating due to some reasons, such as problems when operating a number of units, dampers must be attached to individual extension cones or rectangle to round ducts to prevent the air from flowing backwards. If ducts are separately arranged on the suction side, select fans suitable for individual duct systems. You must be careful when you design a duct to be connected to a high static pressure type axial flow fan. Consult with manufacturers to determine the proper shape of ducts. In particular, note that although NJA axial flow fans save energy due to their high efficiency, fan blades may break and fly out of the fans. This is caused by insufficient duct design, which reduces the speed of fan revolution and changes the wind pressure imposed on the blades. The above explanations are based on the do's and don'ts for design and construction of duct systems. This is the end of the explanation of how to select fans and the shape of the ducts around